Tangential practice number 2, examples. So we're going to do some examples from that particular worksheet. So in the first question here, we're given that AB is 17, BC is 18, CD is 21, which means that all of AB, right? All of AB, there it is equal to, let's change that, 17. BC, this side right here. Now you may be looking at that going, hey, wait, that's not that much longer, or that doesn't look right. Remember, drawing is not necessarily the scale. And last but not least, CD is equal to, so we can draw a straighter line here, there we go, equal to 21. So the key here is to remember, and we're supposed to find AD, so I'll call that X. Remember, that's all of that side, right? Key thing to remember here is in a circumscribed quadrilateral, and we kind of have to assume this because it looks like these are points of tangency, right? That means that the sum of the opposite sides, so x plus 18, is equal to 17 plus 21, which means x plus 18 equals 38. Subtract 38 from both sides. AD, which is our x, right, is equal to 20. And please note, because it is saying a length, we don't need to put the line on top. Similar question here. ON is 7 units, whatever those are. So we'll just label that, that's 7. MN is 24. And angle N is a right angle, label away. Find OQ. All right, so just to make things difficult, they're just asking for that piece. I would argue, hopefully successfully, that indeed these pieces, these points here, are points of tangency, which means that if I'm looking at connecting this and this, these are both radii. And if you look carefully, that would mean that this has got to be congruent to this, which, because this is one right angle and that's a quadrilateral with two congruent sides, that would mean that this side and this side would be, so in other words, we're looking at a square here, which means that these two, and of course we know that these are tangents from an external point, so they must be equal. Now, before we get too far into this, we do need to figure out the length of MO, which means we're going to use the Pythagorean theorem. 7 squared plus 24 squared equals, in this case, let's call it x squared. So let's go ahead and label that x. So what does that mean? Well, it means that I can never remember what 24 squared is. So 24 times 24 is 576. So we know that, hello, cursor, there you are, 49 plus 576 equals x squared. And when you add 49, you get 625, which means we're looking at 625 equals x squared. Sorry, we have to take the square root, which means x is 25. What does that mean? X is 25. Now, we need to come up with some numbers such that this, that is this blue segment and this blue segment, are equal because they're tangents from a common point, and that this, let's go purple, this and this have to be congruent. So we need to come up with numbers such that this piece plus this piece equals 7, this piece, which is the same as this piece, equals 24, plus this piece equals 24. So in the end, we need to try to pick numbers such that when all is said and done, that all the pieces add up to what they're supposed to. So what I'm going to do is do a little bit of what we call experimentation. Now I could set up a system of equations, but I don't think that's going to be that useful because all these numbers end up being nice round numbers, nice whole numbers. So like if I said this was 3, then this would have to be 4 because 3 plus 4 is 7, which would make this 3. Because these two have to be congruent, which would make this piece, well, what plus 3 equals 24? 21. And if this is 21, this has to be 21. Now wait for it. Yeah, I know the answer, so I might have guessed a certain way, but 21 plus what is 25? 4. Does that work? This is equal to this is equal to this, and you guessed it, this is equal to this. So the answer for what OQ is, which is what they actually asked for, is 4 units. The next couple of questions have to do with internal and external tangents. Now remember, with internal and external tangents, it's all about constructing a right triangle. Remember, because they're tangents, that means that these are going to be congruent. So what I'm going to do is I'm going to extend this a little bit and make a line that's parallel and congruent. So if you look carefully, I've formed a rectangle. Now I happen to, and if you look at your notes, you'll discover that this length has got to be the sum of the two radii. I haven't filled the values yet. And the length of the common internal tangent. So the length of the common internal tangent would be this length here, aka this length here. So let's label that x. That's going to be one side. That's what we're trying to find. Now so circle 8. So OP. OP is this line right here that connects these two. Yes? Agree? So what that would mean if I take and let's draw OP and do a nice straight line. Oop. Let's try that again. OP. There it is. There's OP. And that is equal to, let's change its color. Let's make you blue. There you go. Oh, let's try that again. Let's make you blue. That OP, that length there, is equal to 13. Now, they tell us that the radius of the small circle is 3, and the radius of the other circle is 8. What does that mean? This side is 8 plus 3, or 11. So what we've got is a right triangle, and I'm just going to kind of pull that out, where, there we go, there's my right angle. I'm trying to find this matches to this. This side matches to the 11, which is over here, and this side is 13. So, because it's a right triangle, we know x squared plus 11 squared equals 13 squared, so x squared plus 121 equals 169. Then we subtract the 121, which is what? 48. X equals the square root of 48, aka 6.92. And that is the length of the common internal tangent. Key thing, to set up your right triangle, one of the legs is the sum of the two. That is, you add the two radii. And now we're talking about, and I'm just going to jump straight to the end here, we're talking about a common external tangent, so we're trying to find the length of that, so that'd be x. So what that is going to end up being is the leg of a right triangle where the hypotenuse, check that, let's back that up, let's try that again, x, right? Where the hypotenuse is going to be the distance, that is, they're 20 centimeters apart, the hypotenuse is going to be the distance, forgive my drawing, right? And then the length of the common external tangent is going to, one of the legs is going to be the difference between those. So what I can do is I can set up another, and this drawing is not very well to scale, but what I end up doing is setting up a right triangle where one of the legs is what I'm trying to find, the common external tangent, and the hypotenuse ends up being the distance between them, which is 20. And then the length of one of the sides. Now, here's the issue. These are 8 and 10 centimeters, which means the difference, that is 10 minus 8, is 2, which means one of these lengths is only 2 centimeters. And it means that when we draw this line parallel down here, making our right triangle, we get this itty-bitty right triangle, because there's only 2 here, but that is what we're trying to find. So we know that x squared plus 2 squared equals 20 squared, x squared plus 4 equals 400, x squared equals 396, which means x is the square root. Don't forget that part, it's kind of important. Square root of 396, or right around, close to 20, 19.89. centimeters. Key thing, when you're asked to find the length of a common external tangent, it is the difference between the radii. That is, you subtract the radii.